Hello everyone, this is Scicm from Scicm. Today I'm going to talk about nanopipettes and the scanning probe microscope techniques using that nanopipette. Well, generally the scanning probe microscope, we can call the SPM, is utilized very tiny and rigid tip for monitoring sample surface. But also we can use nanopipette as probe for exploring samples morphology and its properties. Okay, let's look into what is nanopipette and how can we utilize it for monitoring nanoworld. Since AFM is developed, various applications of nanotechnology were established, and those applications have led technological advances in many science fields. Using X and Y scanner, three-dimensional information of sample surface can be constructed, and a few nanometer-sized tip scans sample surface by using interaction, like atomic force between AFM tip and sample surface. As shown in these images, researchers can acquire very detailed topography of nanostructure and accurate probe positioning and distance control in nanometer resolution. Based on those benefits from AFM's practical imaging capability, various applications were developed and enabled many innovative material property characterizations. It directly has led to advances in research and industry with successful prosperity. However, those technological advances by nanotechnology has limited in ambient environment. Very soft samples, like biological sample in liquid environment, there is not much successful advances with high impact. Because of unexpected physical contact of AFM tip on sample surface, small and fragile structures can be dragged or scratched, like this figure. Also, AFM tip directly affects to sample's feature, and this may change the condition of the live cells. Of course, this example may be the condition of an actual live cell, but the AFM tip may have accelerated the breakage of the cells intercellular bridge. Like this, using AFM, well, of course, we can obtain the image, but quality is not guaranteed. In this manner, we need another approach. The nanopipette is one of the good candidates for overcoming those limits. Normally, the SPM technique using a nanopipette scans the sample surface by using a pipette with an inner diameter of around 100 nanometer as a probe, instead of very sharp and rigid tip like an AFM tip. The material of a nanopipette is a glass or quartz, and tip end can be customized from tens of nanometer to micrometer size. Let me show you the comparison between AFM tip and nanopipette of SICM, the most famous pipette-based technique. In AFM, very sharp and rigid tip is used, and normally the tip radius is around the tip radius is about 10 nanometer or less. In SCCM, the glass nanopipette is used, and inner diameter is about 80 or 100 nanometer. For the feedback system, AFM, the atomic force between AFM tip and sample surface is utilized, but in SICM, ion current flow between nanopipette and sample surface is used. Looking at the comparison images of AFM and SICM applied to actual fibroblast cells, This confirms that SICM represents even very small features on sample surface very well, like this. But AFM shows these features by crossing them. In addition, in AFM image, the surface appears to be pressed by the AFM tip cell sample interaction. And this actual line profile shows a clear difference from the SICM. From this slide, SPM techniques using a nanopipette will be introduced. SICM, SCCM, and SCCCM. Of course, in addition to these three techniques, there are other techniques using nanopipettes, but considering the measurement principle and application, these are the most famous and useful techniques. The first one is the SICM, the Scanning Ion Conductance Microscope. SICM is a quite good technique for very soft sample, such as a biological sample. SICM uses a glass nanopipette as a sensitive probe based on electrode inside. The inner diameter of nanopipette is typically 50 to 100 nanometer, and two electrodes introduced. One is pipette electrode, and the other one is base electrode. Both electrodes are made of silver colloid, AgCl, and the pipette electrode is inserted inside of the nanopipette, while the sample is placed in petri dish that is typically filled with the same electrolyte. And base electrode is placed in petri dish, and in this setup, if we apply the voltage, it becomes an electrical circuit. By applying a bias voltage between both electrodes and recording the ion current through the nanopipette, locally resolved images of sample topography can be obtained. We always say SICM is true non-contact and non-invasive imaging in liquid, and here is the reason why it is possible. SICM uses the ionic current, which is generated in electrolyte and flow through the nanopipette tip end. It means SICM detects the amount of current signal at the nanopipette tip end. And when the pipette is far from the sample surface, the current is mainly determined by resistance of nanopipette. But the distance between pipette and sample surface decreases. Now, that was the condition. And if the distance between pipette and sample surface decreases, the current begins to be affected by the excess resistance of nanopipette tip opening and starts to decrease. Detecting the current signal, SICM can operate in accurate feedback without pipette probe to sample surface contact. During imaging, the current signal is always kept maintaining about only 1 or 2% current reduced distance by feedback system. This slide shows a good example of why SICM is good for biological sample. Identifying a specific position of highly dense neuron cell area next to the left brain tissue, SICM can acquire the complicated morphology in high magnification and without single contact to sample surface. As you can see on the right side in SICM image, Cells are leach their long arms to the other cells. So they connected each other, forming extremely complicated network structure. SICM can apply not only fixed cell, but also live cell. These images indicate the time-lapse imaging of the cell differentiation process of live cells. It is possible to observe in detail the time-dependent movement of how the protrusions at the end of the cell membrane move for cell differentiation and binding. The next is the SICM, SCCM. The scanning electrochemical microscope, SCCM, is the technique which is mainly for electrochemical response. We can call the EC response. But there is a disadvantage. It is difficult to precisely control the distance between the pipette and sample surface. And SICM, as I said, it is a good method for height imaging with accurate distance control. So, SICM, SCCM, this SICM, SCCM technique combines these two techniques to measure the EC response on the sample surface while maintaining a constant distance between pipette and sample with ion current signal. If only topography is measured like SICM, just a nanopipette is sufficient. But a specially designed nanopipette is required to measure the EC response. In general, based on a nanopipette, a conductive material is coated and the insulator is recoated here. And we called it as ultra micro electrode or UME. At the end of nanopipette, at the end of UME tip, the exposed gold resin, like a conductive material resin, detects an EC response, while this UME tip opening collects an ion current signal for height imaging. So, two-channel information is gathered. The first one is the ion current signal, and the ion current changes according to nanopipette and sample surface distance is utilized for topography, and Faraday current signal on sample surface can be monitored for EC response. For SICM SCCM imaging, the cyclic voltammetry or CV curve first to be measured by combined potential step. After immersing the UME in the buffer, the CV is measured and the SICM SCCM connection is confirmed as a result. The UME approaches the sample surface and measure the CV again on sample surface. Then EC response on sample surface can be monitored. After checking the bias, well, the EC response occurs based on the CV result on the sample surface. The SICM SCCM image is performed while giving the corresponding bias voltage. As you can check this slide, CV curves taken with the AU, the gold crescent electrode in a bulk solution containing EC species before and after approach. Starting from minus 0.15 volt, reduction reaction takes place, and as the potential is ramped up at around minus 0.5 volt. The EC reaction is diffusion controlled and a steady state current is reached at that point. From the CV data, a steady state current was reached at minus 0.5 volt and thus bias applied to gold electrode at minus 0.5 volt or around the 0.4 or 0.5 volt. At that point, it should show dominant contrast of EC response on gold polymer surface like these light figures. Compared with this height image, in height image we cannot recognize this contrast some region on gold and polymer, but in EC this Faraday current like EC response image, we can clearly show the difference between gold and polymer. Okay, the last one is a scanning electrochemical cell microscope, the SCCM. SCCM is a recently developed pipette-based SPM technique designed to investigate the local electrochemical properties of sample surface. Unlike other pipette-based SPM techniques, such as SICM or SCCM, the SCCM utilizes an electrolyte-filled nanopipette to make meniscus contact with the sample surface to create an electrical cell at the end of nanopipette, so that the measurement in ambient condition is possible. For SCCM measurement, an electrode is inserted inside the nanopipette to collect the electrochemical signal. Once pipette approach or contact on sample surface, the meniscus is formed and current signal between pipette tip and sample surface is generated inside the meniscus region. The system detects the signal and immediately stops the G-scanner movement. The EC species in the confined meniscus undergo an EC reaction when a bias is applied between the pipette electrode and working electrode. To visualize the EC response of a sample surface, ARS, like an approach retract scanning method, is adopted to map the target pixel and size. In other words, pipette's linear approach and retract procedure is operated repeatedly on sample surface while monitoring current signal on every single pixel point. At each point, an independent CV is measured and all CV data is gathered to make an EC response image. This slide shows the AFM image to determine the surface morphology and SCCM mapping to estimate the EC signal contrast on sample surface of two different materials. Here's the HOPG and ITO substrate. Using confined meniscus contact at the working electrode, nanoscale imaging can distinguish the EC signal of graphene basal plane, the multi-layered graphene, and the graphene with the conductive substrate. A few layers and step edges are visible using AFM, and contrast shape is well matched with this SCCM mapping image, which shows the EC response of different graphene layers and step edges. The pipette, like a nanopipette-based SPM techniques, each technique has its own characteristics, and a proper technique should be selected and measured according to the measurement environment and purpose. For example, SICM, a non-invasive, like a non-destructive technology specialized for very soft sample. SCCM can measure the EC activities together with the SICM technique. And SCCCM
that can measure EC activity in ambient conditions. Here is the summary of today's talk, and also I want to say, normally nanopipette-based SPM techniques have worse spatial resolution than AFM because the inner diameter of nanopipette is more than tens of nanometer. So compared with the AFM tip, it's quite large. However, nanopipette-based SPM techniques have the advantage of being able to cover applications that are difficult to apply at AFM. So they are being used in various fields such as biology, electrochemistry, material science, and battery research. Okay, thank you for your attention, and any questions are welcome. Thank you.